In this recording, we will extend the energy balance to the operation of a batch reactor. A batch reactor has constant charge and constant discharge. No steady flows of incoming and outgoing streams exist in the operation of a batch reactor. As a result, the species conservation equation for a batch reactor reduces to dNA over dt is equal to Ra times V. Again, we are discussing this for a hypothetical A goes to products type of a reaction. This is the species conservation equation. The energy balance, on the other hand, reduces to du over dt is equal to, this time we have heat interaction in the reactor, and we have shaft work, and we might have surface boundary movement, P dV over dt. This is the first law reduced to a batch system. The necessity of the P dV term makes itself more relevant, especially for systems like an engine cylinder. All right, now we are going to, again, generate a stoichiometric table. This time our hypothetical reaction is going to be, again, A times A plus B times B, producing P times P plus R times R. And our reduced stoichiometric coefficient representation of the same reaction is A plus B over A times B going to P over A times P plus R over A times R. Now there are no inlets, no effluents in this reactor. But again, we have to write a stoichiometric table to be precise in our derivations. So our species are A, B, P, and R. Initially, we have an A0, and B0, and P0, and NR0. And we are going to represent these in terms of their ratio with respect to Na0. As we have done in the previous case, we are going to have this as Na0 times theta B. This is going to be MP0 times theta B. This is going to be NA0 times theta P, and A0 times theta P. This is going to be Na0 times theta R. Initial ratios. And of course, you're going to have a change. And the change is going to be Na0 times X. X is the conversion. The change is going to be B over A times Na0X. The change will be minus P over A times, actually these were going to be minuses and this is going to be plus P over A times Na0X. And this is going to be R over A times Na0X. We're going to use these in deriving the energy balance. All right. Now, as far as this part is concerned, we are fairly clear now how we can use this. We have solved an example. We're going to frame this And we will continue with the energy balance. Let us work on this term, du over dt. What is du over dt for a reacting system? It is d over dt times summation of all the species and I times ui. This is the internal energy. We're going to take the derivative of this. This is going to be summation of d and I times ui plus summation of ni times dui. Internal energy of species I, number of moles of species I. And as far as our reaction is concerned, we have species I, A as A, B, P, and R. Now let's see. D and I. What is it? Is d of ni. It is d of ni0 plus nu I over nu A times na0 x. So if we clarify this for a sample species, say for example D and P, this is D of NP0 plus minus nu I is P, nu A is minus A, therefore we have minus times na0 x. This is a constant. It drops out of the equation and d and P becomes minus P over A na0 times dx. Okay. So dni is equal to, in its most general form, nu I over nu A, the principal stoichiometric coefficient of the principal species. In this case, it is A times na0 times dx. What is dui? dui is C sub v times dt. This is the constant volume heat capacity. This is the temperature in absolute scale. So we collect them together to obtain du over dt to be equal to u sub I times dni summation over all species u sub I times dni, which is nu I over nu A times na0 times dx. And the second term, plus summation of Ni times dui. This is our basis which we will use to derive a general balance equation for batch reactors. General energy balance. Let's continue. Let us substitute Ni from here. Ni is equal to Na0 theta I plus nu I over nu A times X. We're going to regroup the first term. We're going to take the ones that are independent of the species outside the summation sign and continue. Du over dt is equal to Na0 dx summation overall components, overall species, nu I over nu A times ui plus the second term, Ni, Na0 theta I Na0 times theta I plus nu I over nu A times X times dui. Okay. Let us define our expressions. If we remember from our previous recording, from the enthalpy side, a similar term has appeared in our equations. This term we identified as minus delta H of reaction. This term is now our minus delta U of reaction. So our expression is becoming more compact. Let us apply the same analogy here we have in this term. Let us expand this term only. Summation of Na0 summation of theta I times dui plus Na0x summation of nu I over nu A times dui. And if this is delta U of reaction, we are going to come up with a similar explanation for this term. Now we continue. I have transferred the expressions that I have derived here right underneath the du over dt term. We have du over dt comprised of three terms. The first term is Na0 dx times minus delta U of reaction. The second term is Na0x summation over nu I over nu A dui. And the third term is Na0 summation of theta I times dui. This term has a striking similarity to this term. So if I just take these inside the derivative sign, I obtain d minus delta U reaction. All right, dx over dt, we have to be precise, d over dt, dui over dt. All right, so this crowded domain looks like this. Du over dt is equal to Na0 d over dt x times minus delta U reaction. I have combined these two terms. These two terms can be combined as such, plus Na0 summation of theta I dui over dt. So this is the most general form of the internal energy term of the reduced first law expression for a batch reactor. Now we continue with a more cleaned up space. We have du over dt expressed in terms of the delta U of reaction, the stoichiometric ratios of the feeds, and no, there's no x here, sorry. There is no x here. And then A0. All right. Now we are going to substitute for dui over dt as a Cv dt over dt in order to have a more compact expression of du over dt as Na0 d over dt x minus delta U reaction plus Na0 sigma theta I dui over dt is going to substitute from here times Cvi dt over dt. Now this term can be taken out here. It is common for all the species, and we are left with a term called theta I Cvi. So theta I is the feed stoichiometric ratio, Cvi is the constant volume heat capacity of species I. This is going to be the average heat capacity of the feed. So in its most compact form, du over dt term reduces to Na0 d over dt x minus delta U reaction plus Na0 mean heat capacity of the feed times dT over dt. This is the first part. The right-hand side of the equation is equal to Q plus shaft work minus P dV over dt. This term, dV over dt term, can also go through the same kind of algebra as this term, du over dt. To begin, I will write the first step, and I will expect you to complete the rest. This is going to be du over dt summation of all the species Ni times Vi. Just like we have started from du over dt as the summation of Ni times Ui, this starts as d over dt summation Ni dot Vi. Please follow and finish this derivation for the V term. So we have our expression in hand. We are going to use this expression to derive the energy balance equation for an adiabatic constant volume batch reactor. Energy balance for an adiabatic in other words, the Q term is equal to 0, constant volume, in other words, dV over dt term is equal to 0, batch reactor. Our reaction is the same. Our species conservation balance is here. Our energy balance is going to simplify according to the constraints that we impose upon this system. Q is equal to 0. This term is going to drop. Volume is constant. This term is going to drop. And we are going to have two terms, three terms. This term, this term, and the shaft work term. So let's translate that information over here. I'll take Na0 out, take a big frame, X times minus delta U reaction, plus CV average dt over dt is equal to shaft work. Shaft work enters into the picture through the impeller. Shaft work may not constitute too much for the situations where we are not dealing with very viscous fluids, but if we have viscous fluids in the reactor, shaft work may constitute a significant component, constitute a significant amount of the overall energy. So for the sake of the first example, I will approximate the shaft work negligible in comparison to the other components. I did not specify whether I have a gas phase reactor or a liquid phase reactor. None of these were specified. This is just the general energy balance we are solving for an adiabatic and a constant volume batch reactor. Yes, now if this term becomes 0 and a 0 term drops out of the equation that we have, then d over dt x times minus delta U reaction to be equal to minus Cv bar dt over dt. The internal energy change due to the reaction can be considered independent of temperature and conversion, and can be taken out of the derivative sign. So we have minus delta U reaction times dx over dt. We dropped dt's, the previous step, is equal to minus C sub V dt. All right? This is equation number 1. From the species conservation equation, for a constant volume batch reactor, we are going to bring in d Ca over dt to be equal to Ra times V. This is a constant volume batch reactor. V went to the other side of the equation, entered into the derivative, and Na over V became Ca. And we are going to solve this problem for a hypothetical first order reaction, which is K times Ca. And K is equal to K0 e to the minus Ea over RT times Ca is equal to Ca0 times 1 minus x. On this side, we have minus Ca0 dx over dt. So perhaps it might be useful to maintain the dt terms in here so that we are going to have coupled ordinary differential equations. We have two unknowns. One is conversion, one is temperature, and we have two equations, one coming from the species conservation and the other one coming from the first law. All right? So when we substitute dx over dt from here in this expression, we have an expression relating temperature to conversion. All right? Solution of these coupled differential equations are sometimes non-trivial, but let me transfer this underneath the energy balance so that we can see everything in a clear and concise fashion. Minus Ca0 dx over dt is equal to K0 e to the minus Ea over RT times Ca0. In fact, Ca0s cancel, so I will erase this one, minus dx over dt times 1 minus x. So in order to solve this equation, we need initial conditions at time t is equal to 0, x is equal to 0, no conversion, and t is equal to t0. All right? Becoming familiar with the solution of coupled ordinary differential equations by numerical methods is going to take you far, and that is strongly recommended. So the terms in the frame represent the summary of energy balance around a batch reactor. You have two assignments. One is to derive the equivalent expression for dV over dt term, because things will get complicated when we have a constant pressure batch reactor, such as a diesel engine operation. And the first assignment is to derive dV over dt, and the second assignment is the analytical and numerical solution of this coupled differential equation. So I hope that your answer, I'm sure that your answer is correct, that now you're able to come to the solution part of the coupled differential equations. The first equation, the energy balance, actually is fairly straightforward to solve. One side is only a function of temperature, the other side is only a function of conversion, and everything else are constants. So I'm going to regroup the terms delta U over delta U reaction over CV average times dx is equal to dt, and we are going to integrate from t0 to t, from 0 to x. So we have delta U reaction divided by C sub V times x is equal to t minus t0. Now this expression relates temperature to conversion. Why do we need such an expression? Because we have a temperature term in the species conservation equation. We are going to substitute this term in that temperature and solve that for conversion. So T is equal to T0 plus delta U reaction divided by C sub V times x. And that term is going to enter minus dx over dt times k0 e to the minus ea divided by r times t, this term, T0 plus delta U reaction divided by C sub V times x times 1 minus x. Now this is an expression with only x as a variable, which can be solved given the initial condition at time t is equal to 0, x is equal to 0. Today we are going to learn how to conduct the energy balance around a batch reactor under constant pressure constraints. Again, we will start from the species conservation equation. We have dNA over dt, that is equal to RA times V. Under constant volume constraints, we were able to transfer this V into the expression. However, our constraint is constant pressure. But today I'm going to have an additional constraint, which I will come back later to the species conservation equation. Let's leave it like this. Let's derive the energy balance equation. So here on this side we have a material balance. And the energy balance for a batch reactor is du over dt. That is equal to net heat exchange, shaft work, and PdV over dt. Under constant pressure conditions, we can write this as dPV over dt. We can transfer it to the left side of the equal and bring with the internal energy term to obtain U plus PV. That is equal to Q plus shaft work. This term is called the enthalpy. dH over dt is equal to Q plus shaft work. So this is the first and most rigorous way of bringing the terms together to have the reaction energetics in terms of an enthalpy variable but we have to also keep in mind that under constant volume conditions for incompressible fluids, such as liquids, dV over dt term is approximately 0, and dH over dt is approximately equal to du over dt, and as a result, heat capacity at constant pressure is almost equal to the heat capacity at constant volume. So here I'm going to continue for the condition where we have an incompressible fluid, because we have to develop descriptions, equations, rigorous equations to take the volume change into account. I haven't done that yet, so we're going to proceed with an approximation that we are dealing with an incompressible fluid. As a result, we have d over dt Ca to be equal to R sub A. Now I'm going to derive the expression for the dH over dt, just like we have done for du over dt. And using that expression, we will discuss the unstabilities that we can encounter, the multiple steady states that we can encounter in a chemical reactor. So on this side, let's again dissect the H into its constituents. And obtain the final expression as we have done yesterday. So again, starting from the same expression, by the addition of the adiabatic constraints of an adiabatic reactor and negligible shaft work, we are able to derive the temperature change within the reactor as a function of conversion, enthalpy change of the reaction, and the mean heat capacity. Mean feed heat capacity. The temperature expression is substituted in the Arrhenius expression, and as we understand from this, as the reaction proceeds, temperature increases. Now let's come back to the material balance side. We are working for the incompressible fluid condition, and for the incompressible fluid, for a pseudo first order reaction, Ra is minus K times Ca, and our time progression of this reaction for a batch reactor takes this form. And of course, since our temperature is a function of x, we are going to convert concentration to the equivalent expression in terms of conversion, remembering that Ca0 minus Ca divided by Ca0 was equal to x, or Ca was equal to Ca0, 1 minus x. Or dCa over dt is equal to minus Ca0 dx over dt. Such that we have minus Ca0 dx over dt to be equal to minus K0 e to the minus e over r times t. T is equal to T0 plus delta H over Cp mean feed heat capacity times x. Now instead of a temperature variable, we have a conversion variable in the Arrhenius form times Ca0 times 1 minus x. The negative terms cancel, CA0 terms cancel, and we have a nonlinear ordinary differential equation to be solved with the constraint when time is equal to 0, with the initial condition time is equal to 0, x is equal to 0.